I know I got a good match. So there's my peak. I'm going to make sure that I really am on the center frequency. I am. Adjust my gain so that I'm right on 1.0. Now as I move this to the left, that's my minimum right there. So what's my SWR? Not sure why it's bobbling right there, but looks like it's about 1.06, right? If that's 1.1 right there, that's 1.0, 1.02, 1.04, 1.06. Let's see if the expanded scale works on this beast. Now I can look at it on my expanded scale. It looks like it's 1.05. Would you call that a good match? Sure you would. That's essentially what you did in experiment number 8. The setup doesn't look the same because a lot of what you had to have in front of you is actually inside that instrument. But it's taking a reflection coefficient, an S11 S parameter measurement, and notice that we were able to see where the slide screw tuner looks like already a partially matched impedance because the resistor portion is equal to the characteristic impedance of the waveguide, which fortunately is about 50 ohms because this instrument is designed to work around 50 ohm impedance. Then the slide screw tuner is only going to have to tune out the mismatch, and notice how much of an effect it has. Here I'm playing around with the depth, and notice how much that is affecting the apparent match on there as well as the SWR. And during the break, I encourage you to come up here and try this for yourself. Notice it does not take much movement to have a very large movement along either the resistance or the reactance portion of the axis. One other thing, I'm not going to put the numbers up on the board, but I have them up here. I, before class started, actually made a measurement of what the reactance was at a number of positions in which the slide screw tuner I really moved it out of the right position. Be right there. No. Well, if I get back to where it's supposed to be and I completely withdraw the probe, then we can see how much reactance is present. That's what I'm trying to do, but I need to make sure I'm in exactly the right place. And so here the probe is at position 0 again. Okay, now the SWR meter is definitely going to show an SWR. Notice that I definitely have a mismatch now, right? But notice that I also can read directly what the conductance and susceptance are. And if I go back to my Smith chart, it looks like I have about 20 ohms of capacitive reactance in here. Now, I did the calculation, or I did the measurements at some point before, and I saw that at one time when I did this, at about 6 millimeters of insertion is about where I would see 25 ohms of the opposite type of reactance that I would need to dial in to achieve the match. So going back to my matched state here, and again, I know I found the right place where I can see that pointer always stay on the circle. That's how I know I didn't just luck out. Notice that that's a bit of a challenge. I know it may be a little bit hard to see from where you're sitting, but I'm not moving this even as much as 0.5 millimeter every time I make an adjustment. But at some point along here, I would find that, and I encourage you to come up during the break and try this if you want, you'll see that you place in between 4.5 and 5 millimeters of penetration depth in order to get the matched condition. And that is exactly where you would predict the amount of the opposing type of reactance that needs to be included would have to be based on the measurements that the instrument is producing for reactance based on penetration depth. And indeed, that confirms that we have matched our impedance by putting in the opposite type of reactance. That's really what the last part of this. Now, one last thing. I know I'm running a little bit long. It looks like we're very close to our matched condition, right? Right about there. I know if I move it now, I'll never get it back right. Let me try to really zero it in. Right about there. That is position 63. Now what if I moved 18 millimeters to the right? Shouldn't I see a match there as well? Everything repeats itself every half wavelength. Let me try that. Wasn't that the same place you found in experiment 8? Mm-hmm. Almost right on the money. Surprised even me when I first set this up. Wow, it worked. Okay, that's what I wanted to show you. That's basically what you've been doing all this time. Notice the network analyzer allows you to visually see a number of things. One is that a millimeter makes a big difference at these frequencies, doesn't it? Another thing that's a big factor is the depth of penetration of this slotted line detector. Remember I told you don't put it in too deep. Watch what happens if I play with that depth. Notice that even that, and I have it in about as far as I've asked you to have it all this time, can have an effect on it as well, can it? So you don't want to have it in really deep, that's all the way in, because notice that is affecting the accuracy of your measurements quite substantially. So where you pretty much had it all this time is, I think, very close to ideal. And so that's where I'll leave it. And that's pretty much where I want to leave you. That's basically what I wanted to demonstrate, is showing how an impedance match in waveguide actually looks visually. And that's what you did in experiment number 8. You got to this point by finding the specific location, which is position 44. That's almost exactly where we are now. Okay? That's because now, at this location, the probe looks like a pure conductance. I'm sorry, pure susceptance. The conductance is already equal to the conductance of the matched network. All right? Any questions, comments, death threats?